Hello, students. Um, so upon my email, sorry the video is not great, but hopefully you can see that screen well enough. There's the main thing. Um, I'll be not in class today. So what I'm going to do is I'm just going to record a lecture that'll cover the content that we would cover in class. I'll split it up into a few pieces for ease of digest. So let's go ahead and get started. So I've got a few more things to say just in the section on group theory. I've got lots of things to say about groups. That's what we're going to be talking about for a while yet. Let's talk about cyclic groups. So we've already given the definition. What is a cyclic group? A cyclic group is no, let's not use that. Here's the one I want. What's a cyclic group? A cyclic group is a group that's generated by some element. And what does that mean? That just means everything in the group can be written as some power of that element. And, well, we've done a few things. We showed that if G is a generator, then so is G inverse. So that makes a lot of sense, I think. If you can get anywhere by just iterating G in the forward and backward direction, that's the same as getting everything by getting G inverse, iterating in the backwards or forwards direction. There's an abstract group called the infinite cyclic, the cyclic groups. And what is it? The infinite cyclic group is just things that look like some abstract variable called A with a K in the superscript, all just defined to behave the way you think. A raised to the K times A raised to the L is now defined to be A raised to the power K plus L. On the other hand, the cyclic group of order n is defined the exact same way, except now I'm only going to allow powers between 0 and n minus 1. I'm going to do multiplication, not by addition per se, but somehow by doing addition mod n. So this m is the sum of k and l mod n, but it's the representative that's between 0 and n. Nice. So I think in class we talked about why Cn is actually cyclic, and let's just see. So any element of Cn is of the form a to the k for some k equal to 0, 1, 2, dot, 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 n minus 1. That's just by the definition of what ck means. But, and maybe here's a good observation to make, by a straightforward induction, a to the k is the same thing as this abstract symbol called a upper 1 raised to the kth power. And you feel like all that this induction is saying is that this a upper 5 really does mean the same thing as taking a upper 1, the thing that you'd want to just call a, and iterating it 5 times. As another observation, Z is cyclic with multiplicative notation. And I want to emphasize this because this is going to highlight using additive notation when appropriate instead of multiplicative. So maybe here's the thing to say aside. In additive notation, we say n times x instead of x to the n, meaning the same thing. So this x is the element of the group G, and this n is the power to which you're raising it. There's the element of the integers. And right, of course, that makes total sense, right? Like multiplication of integers means iterated addition. Exponentiation means iterated multiplication. So this analog makes, I think, pretty good sense. So let's prove that. So let's see. For any n in Z, I need to show that n can be written by applying the generator, which allegedly is 1 a bunch of times. And well, of course you can. For any n in Z, you can write n as n times 1. So any n in Z is a multiple of 1. And that's not deep or new. That's something you already knew. But that's what cyclic means. Cyclic means you can get anywhere by starting at that 1. Oh, and I guess I should have underlined that one. The proof for Z mod n is the same. All right. So cyclic groups are very special groups. But when you have groups that aren't too big, it turns out there aren't many groups of small size. As the size of a group grows, the number of groups get bigger and more complicated. But it turns out for small groups, they're cyclic. And we'll prove something more general than this soon. But here's a theorem. If the size of a group G, and as a reminder, I think we established this on the other notes, when I say big G, I will mean a group. Then G is cyclic. So let's prove that. So what are the numbers that are less than or equal to 3? Well, the empty set can't be a group because a group has to have an identity element. The empty set doesn't have an identity element, so that doesn't count. Group with only one element. So if the size of G is 1, then G has only one element. It definitely has an element called E, the unity element. So it only has one element, and I've just specified what that element is. It's the unity element. So G is equal to just the identity element. Explain why that E generates all of G. Well, what do I need to do that? The only element of G is E, and E is equal to, well, I guess it doesn't matter what power I pick. Let's say E to the 1 is a power of E. So what can I conclude? I've now concluded that every element of G is a power of E. That means that G is cyclic, generated by E. In fact, here's a tangential claim. Try to prove this. If a group is cyclic, generated by the identity element, then that group only contains the identity element. So this is the only time that that particular thing happens. Secondly, if the size of G is equal to 2, then G contains 2 elements. We already know what one of them is. It's E. It's got one more element. Let's give it a name, G. So if the size of G is 2, then G is equal to the set containing E and G, where E is the unity element, and you have some other element called G. I claim that G generates. So I need to show that every element of this set big G can be written as a power of little g. All right, so let's I don't know, I'll call it X be in G. There are now two cases. Then either X is equal to G. Ooh, but that's a power of G. That's G to the 1. So X is a power of G. That's exactly what you need. And let's fix this grammatically. I mean, you know what I'm going for. Well, maybe you don't. Either x is equal to g or x is equal to e. So this is going to be like case-wise. In case one, x is equal to g to the 1. So x is a power of g. Cool. All right, so the other case is that x is the identity element. In case 2, x is equal to the identity element. Ah, but that's also a power of g. That's g to the power of 0. Anything raised to the 0 is just defined to be the identity element. So x is a power of e. In either case, x is a power, well, not a power of e, power of g. So what's the conclusion? Thus, big G is cyclic, generated by G. Nice. All right, so in the case that you have 3 elements in your group, the proof is just a little bit more complicated. It shouldn't be surprising. As the number of elements grows, you have more things to worry about. Um, I might even say, if you would like, pause the video, go through and compose a proof of this. Cool. All right, you did that. So you came up with your proof. Let's write up a proof right here, though. So let's see how it compares with yours. All right. So suppose the size of G is 3. So it's got 3 elements. One of them's the identity element. There's something else, G. There's something that's different from those two things, H. Let's list those 3 elements. Here's the first step that I propose. Let's prove that G times H is equal to E. And I'll use a proof by contradiction. So let's write it. So if GH is not equal to E, it could be one of two things. It could be G or it could be H. So I guess that's in parentheses. So that doesn't count as part of the proof. So let's proceed by contradiction. That should be a full stop at the end. If GH is not equal to E, then either GH equals G or GH equals H. And why are those the two other only cases that are left? Well, this is a group, so it's closed under multiplication. I just said that GH isn't equal to E. There are only 2 other elements of this group, G or H. Ooh, but let's look. Let's label the cases 1 or 2. In case 1, well, let's see. I can take that GH, give myself some space. I can multiply both sides by G inverse. So H is equal to E. Oh, but that's upsetting. But this contradicts that E, G, and H are the 3 distinct elements of G. Or maybe, for emphasis, I'll underline distinct. And what do I mean there? Well, this group G has 3 elements, and I said that those 3 elements are E, G, and H. If H was just equal to E, then this group only has 2 elements. Thus, GH is not equal to G. We get a similar contradiction if GH equals H, thus GH is equal to E. Ooh, but what does that mean? This means H must be equal to G inverse. Aha! H is a power of G. Oh, but the other two elements are also powers of G by the same argument as we already used. As E is equal to G to the 0, and G is equal to G to the power 1, comma, every element of G is a power of little g. Very good. So, this might seem like I'm trying to build up towards a pattern. You might say, this must mean that like all groups are cyclic no matter how many elements they have, but that's not true. Groups can get really complicated. In fact, maybe here's one for you. Prove that the symmetric groups are not cyclic as soon as n is at least 3. Prove that the symmetric group on three things is not cyclic. I'll prove a simpler thing. So here's a group with 4 elements, Z2 cross Z2. This is cyclic. Has only 4 elements. I claim it is not cyclic. And let's see why. And you know what? Let's actually just go down here and do some scratch walk. So what are the elements of Z2 cross Z2? Well, they're elements that look like something pulled from Z2, comma, something pulled from Z2. So listing all of those things, well, it's 0, 0, 1, 0. Maybe I should put lines on top of them. Yeah, because it's Z mod 2. 0, 1, 1, 1. So there are 4 elements. I need there not to exist a single thing that generates. Let's see if any of those things generate. Let's see. Let's see if 0, 0 generates. Oh, 2 times 0 is 0. Oh, that's no good. Okay. So the things generated by 0, this is the first line now. So I guess I'm going to go up here into the proof. If this thing was cyclic, then there would be some element of the group that would result in the set of all multiples of that thing, x, give you all of Z2 cross Z2. So we're just going to eliminate all the possibilities. If x were equal to 0, 0, then, well, I guess that's not surprising. The things you can get by multiplying 0 by any number just give you 0. Take a moment and fill out the rest of these. So what are the multiples of 1, 0? Let's see, so that'll be 2 times 1 bar. So meaning 1 bar plus 1 bar. Oh, wait, 2 times 1 is 0, though. So I'm marking in Z mod 2. Oh, so I made it back to 0. Now let's see what I multiplied by 3. So that's 3 times 1 bar. Oh, let's put the parentheses correctly. Ooh, 3 times 1 is 3 mod 2. That is 2. Nope, 1. Oh, so I got back to where I started, and maybe now you believe that if I just keep iterating, add this to itself, I'm just going to keep alternating between 1, 0, and 0, 0. Oh, well, same thing will happen here. Oh, that's a bummer. In each case, I only get two elements in the set of all things that are multiples of that x. There are four things in this set, z2 cross z2. None of them give me all of z2 cross z2, so z2 cross z2 isn't generated by any element of z2 cross z2. It's not cyclic. And this is like the simplest example of something that's not cyclic. It's only got four things, and I know that everything that has at most three things is cyclic. Cool. So I'm going to stop the recording for now. There. I'm going to point out that there's some homework to be done. And I'll meet you in a moment while we talk about subgroups. Let's stop the recording.